Okay, so this is going to be a review of example 8. We started this in class, but we weren't able to finish it, and so I would just want to go over example number 8. I'm going to do a separate video that goes over example number 9. But again, I just want to kind of finish this one up because we didn't get to finish this one in class. So example number 8, this is logistic growth, and it gives us this question. Suppose that a population develops according to the logistics differential equation dp dt equals 0.2 p minus 0.002 p squared, where t is measured in weeks and t is greater than 0. And so then it gives us a couple of questions here. And it says for A, if p of 0 equals 5, what is the limit as t approaches infinity of p of t? And then for B, it gives us if p of 0 equals 60, they want to look at the limit. And then C, if p of 0 equals 120, what's the limit as t approaches infinity? So I want to ask the first question. We're looking at this differential equation, and it's a logistics differential equation. They gave us that in the problem. But I want to ask the question, does it matter what the y-intercept is? They're all asking for what the limit as t approaches infinity is. So does it matter what the initial value of the problem is going to be in this particular problem? No, it's not. It's not going to matter what the initial value is, right? All we're concerned with is as t goes towards infinity, what's going to happen with this problem. So we don't really care where we start from, if p of 0 equals 5 or 60 or 120. What we care about, at least in the first part of this, is what happens when it goes towards infinity. So for this first part of it, we don't really care what the initial value is. What we do know is that they're all going to approach the limit, right? We know as they all go towards infinity, based off of our rough sketch of a logistics growth model, right? We know roughly that a logistics growth all is going to approach some kind of limit, right? So we have a limit up here. This is my limit. And we know that a logistics growth model looks something generally like this, right? So we know that the limit is what's going to happen. So as these all approach infinity, they're going to all approach this limit right here. So the question becomes in this problem, what is the limit, right? So what we need to do for at least for the first part of all three of these is uh, we need to get L. That's what we're looking for. We're looking for that limit. We're looking for L. Now, we've worked with this a little bit so far. And what we've done when we've worked with this is that we've gotten the logistics problem in a form where dp dt equals k times p in parentheses L minus P. Okay, and this is what looked familiar to us. And currently what we have right now is dp dt equals 0.2 times P minus 0.002 P squared. And that does not look like what we have. And so what we want to do is get this in the form in which we can manipulate this, get this in a form that looks comfortable to us and looks somewhat familiar to us, in which we can then have our K's and our P's. And in fact, we can do that. If we take the formula, if we take what they gave us, which was dp dt equals 0.2p minus 0.002 p squared. Well, we got to ask ourselves, what do we got to do to this equation to get it in the form that we're comfortable with, where we have in a parentheses the limit minus just a single p? Well, we have a p squared going on here. And in fact, we have another p here. So we can pull a p out of this and get it down to just a p inside the parentheses. So let's do that. Let's take a p out first. That'll be the first step we can do. So dp dt equals, well, we can take a p out, right? So we can do that. We got 0.2 minus a 0.002 times p. Okay, so all I did was I took a p out. Hey, we can do that. Well, in fact, we can go one more step further because we want to get this P right here, this one, by itself. And so that it looks like this form here, where we've got an L minus just a P. And we've almost got that. We've got a P being multiplied by something, and we don't want it multiplied by something. We want to have it by itself. And so let's do one more thing to this. What we can do is we can take this scalar right here, this 0.002, and take that out too. And so what we're left with when we do that is dp dt equals, well, on the outside of this equation, we've got, what do we've got? We've got 0.002p times, well, inside of this, we get, I'm going to do the math over here. We got 0.2 divided by 0.002, okay? So 0.2 divided by 0.002, and truthfully, that's something that's a little bit above what I'm going to do mentally. So I'm going to pull out a calculator. zero point 0.2 divided by 0.002, hey, that ends up being 100. Okay, so I've got 100 on the inside minus just a p because I took that 0.002 out intentionally. Well, wait a minute here. Now this is in a form that we're comfortable with, right? We've got a k times a p, and inside the parentheses, I got an L minus a p. Well, that's handy for us. That's something that we can work with here. I'm going to take that out. And so now the question becomes, we needed to get the L, right? They were asking us what the limit was. And now that we've got this in a form that we're comfortable with, what's our L? Well, hey, our L is right here. Our L happens to be 100. So what's the limit? Well, the limit is 100. Okay. So that's the first part of this. For A, B, and C, it doesn't matter what our initial starting value is. What it matters is what's the limit. When t approaches infinity, what's it going to go towards? Well, it's going to go towards 100. Okay? Okay, so now the second part of this. Sketch the solution curves for A, B, and C, and which one has an inflection point. Okay? So this is an interesting portion of the problem. So what we're going to do is we're going to use this equation right here, this dp dt equals 0.002p and the 100 minus p. That we needed that bit of information. In fact, we needed this limit of 100 bit of information. And we needed it so that we could get this inflection point. Now, if you recall, I told you in class that every logistics curve had an inflection point. And if we talked about it, generally speaking, when we were talking about it, generally speaking, there was the limit at the top right here, right? And then there was a curve that we drew. And there's this point right about here in this picture. And it's a point in the curve where it goes from concave up to concave down. And it's an inflection point, okay? And that inflection point always equals the inflection. I'm going to write this down for you. Inflection point is always equal to L divided by 2. Okay, so that inflection point is an important point for us. The inflection point is always going to equal L divided by 2. And so for us, let's find out what that inflection point is going to be for our particular graph here. So our limit is 100, our L is 100, and so our inflection point in this particular one is going to be 100 divided by 2, which ends up being 50. Okay, so that's going to be an important bit of information for us. Okay, so let's see if we can't draw some of these. So they gave us some initial starting values, and that's going to come in handy for this particular graph. So it says for the first one, if p of 0 equals 5, so we're going to draw this one. So for A, p of 0 equals 5. That's my initial starting value. So I'm going to kind of sketch this out here. And we've got a logistics curve, and I've got a point here at the top, my limit, top here. So my limit, this is 100, right? That's my limit. That's the point at the top. And I've got my inflection point here, my halfway mark, that's going to be 50. Okay. And so I'm going to kind of eyeball this here. Somewhere around here is going to be my starting value. My P of 0, this is going to be 5. It's going to be very, very low. And so what I'm going to do here is for this particular one, I've got a starting point that's going to go up like this. And then somewhere around where this point hit 50, it's going to go from concave up to concave down. And again, we're working with Mr. Peak's drawing skills, which we all know are somewhat sketchy. Okay, so we started right here and we kind of went curved up, and then we had that little bit of a curve to the right. Okay, so that's what that first one's going to look like. It starts at that 0.05, curves up, and then kind of flattens out towards as it gets towards that limit. Now for part B, or for question B rather, it said that P of 0 equaled 60. Okay, so again, we're going to draw this out as best we can, or as best I can. Again, we've got my limit up here at the top, which is 100. I'm going to draw my halfway mark, which is 50. And now my starting value is P of 60. So I'm going to start above that point there. So I'm going to start somewhere, let's say here. This is going to be 60. Now, I'm above this inflection point. This inflection point is where it went from concave up to concave down. So because I'm starting here, my curve is just going to look like this. Okay, it's just going to have that concave down look to it. Okay, there's no concave up on this because I started above that inflection point. And again, let's do part C. Now part C, P of 0 equals 120. Okay, and my limit here is 100. Now my inflection point here is what, about 50. Now my starting value here, P of 0 is 120. That's above my limit, right? That is going to put me, I don't know, let's say right around here. This 100, it's 120. Okay, so my starting point is going to be above here. It's going to be starting up here. What's my curve going to look like? Well, remember, with a logistics curve, we're always going towards the limit. Okay, we're trying to strive towards the limit. And so this isn't going to go exponential. It's not exponential growth. It's not going to keep growing. It's trying to get back towards that limit. And so what this is going to look like, in fact, is that it's going to kind of curve down. Try to, let's try to redraw that a little bit here. Try to draw that so it's curving down. And so it's going to curve down towards that limit. And it's, again, trying to approach that limit. And so it should have a little bit of a curve down. Now, here's all three of those curves, right? We've got A, B, and C. Now, the second part of that question, sketch the solution curves and which one has an inflection point. So if we look at our three curves here, right, we've got P of 0 is 5, P of 0 is 60, and P of 0 is 120. We only see one of these where we see it curves up and then it curves down. So in part A, we started below the inflection point and we have the inflection point actually occurring. In part B, it doesn't have that, right? We started above that inflection point, so we only had concave down, and in part C, we were actually above the limit, and we were striving to get down towards it. So the only one that had that inflection point was, in fact, part A. And so if we answered that and that part D, which one has an inflection point? Well, that one would have been part A, or sketch graph A. P of 0 equals 5. And which solutions are strictly increasing or strictly decreasing? Again, if we're looking at our graphs of this, it looks like and it appears that B is going to be strictly increasing. It's constantly trying to go towards that limit. C is strictly decreasing, right? It looks like it's trying to go down towards that limit. Let's look at graph A. Graph A is an interesting one, right? It looks like it is constantly increasing as well. And so A is one it's a little odd. It's going to be constantly increasing and going towards that limit. Even though we have a concave up, concave down, it is continually increasing to get towards that limit. So A would also be one that is continuously increasing. Okay? And so it's just something to be aware of, something to look at when you're looking at these graphs and thinking about what these are doing. Okay. So again, when we were looking at the limit, all three of them had the same limit. They were all trying to get to that same limit. But when we were sketching them, only one of them ended up having the inflection point because of the starting values. If you have any questions, please, please, please reach out and let me know.